Okay, I put it start. Okay, so hello everybody. So welcome to CADEP seminar. It's slowly growing. Every week we have at least one new or two new persons. So today is going to talk Javier Gargiulo about pullback of toric foliations.
Okay.
Yeah. So let's start.
Okay. Thank you, Hussein, so much for the invitation for giving this talk. So here. What's that noise? Okay. Okay. So I'm going to talk about rational pullback of toric foliation. So in general, I don't know how much to assume in this seminar about foliations and about toric varieties. So if you have any question regarding these two topics, just stop me and I can say more about that. Okay. So this is a joint work with Molinuevo Ariel, who's a professor at the UFRJ, Velázquez Sebastián, who is a PhD student in Buenos Aires, Argentina. Okay, so the plan of the talk is just to make a short introduction to the theory of toric varieties, foliations on toric varieties, and rational maps between them. These are going to be the keys to understand the rest of the talk. And the idea is to produce examples of singular projective foliations using this setting. And I'm going to talk about two families of singular projective foliation that arise in this way. The first is just the foliations given by the fibers of rational maps. And the other topic is just consider a foliation on a toric surface and considering its pullback by a suitable family of rational maps to a projective space, to the classical projective space. I don't know if I'm going to have many time to talk about this first topic, okay? For me in this talk, I'm going to denote by x sub t to the q for a simplicial complete toric variety of dimension q. So a toric variety is just an algebraic variety which contains a torus t as a statistically open set in such way that the natural action of this torus on itself extends to an algebraic action of the torus on the whole variety x. Okay, so examples of this type of varieties are just the classical projective spaces, weighted projective spaces, product of projective spaces, Hirzebruch surfaces, and so many other. And the idea behind this, the idea of working with this type of varieties, in particular in foliation theory, is that in general, this is a guiding principle, no? A toric variety is a geometric object that has an associated combinatorial and simplicial object called a fan, and most of the geometric properties of the toric variety can be described in terms of combinatorial things in the right side according to the fan. I'm not going to explain this construction in general, but just to fix the notation, let me show you how to construct the classical projective plane using a fan, okay? Just to understand the general setting, okay? So, a fan is just a collection of rational polyhedral cones of different dimensions. I'm going to fix in general a standard lattice of Rn, in this case is R2, okay? And I'm going to draw here different cones of different dimensions, okay? Just the zero dimensional cones are just the point zero. The one dimensional cones are these rays, B1, B2, and B3. And the two-dimensional cones are just painting everything in between these rays, okay? Sigma 0, sigma 1, and sigma 2. This, in some sense, this picture is complete. And for example, this in particular implies that the corresponding toric variety that you can construct, in this case P2, is complete and as a geometric object, as an algebraic variety, okay? Another important fact using the information here is that, let me observe that you have in general, you have three rays, but in this construction for P2, you have three rays, three one-dimensional cones, okay? And that the unique relation between these vectors, B1, B2, and B3 is the relation 1, 1, 1. Okay, So how to use this picture to construct in general toric variety? Okay, to each cone, you have a standard or a natural way to associate it an affine space, okay? So to each cone, you can associate an affine space. In this case, to the maximal dimensional cones, sigma 0, sigma 1, and sigma 2, you can associate the following affine spaces. And if you look at these spaces, these are the standard covering of P2 using the affine charts, okay? And in some sense, these are associated to the maximal dimensional cones. And the lower dimensional cones, in this case, B1, B2, and B3, say you how to view these affine charts into obtain a global object, okay? This is just the general idea to construct using a fan and a toric variety, okay? Another important fact in toric varieties, or in this case, is that you have the possibility of construct a quotient or describe them by a quotient. In this case, P2 can be constructed just as the space C3 minus 0, and you need to take the quotient by this torus to 3 minus 2, where these numbers that appear here are just associated to the dimension of the variety and the number of the one-dimensional cones. Okay, and another important fact about P2 is that you have, in the affine cone, you have this vector field called the radial vector field, which in P2 is trivial, okay? And the coefficients of this radial vector field are just ones and are associated to this relation among the rays, okay? Okay, another important fact is that this variety is smooth, so the class group coincides with the Picard group, and it's free of the Picard number is just 3 minus 2, again the number of rays minus the dimension of the variety. And you have this homogeneous coordinate ring, in some sense called the Cox ring, which is graded, which is C graded. This C that appears here is just the class group of the variety, and the degree of each of the variables is again 1. These ones are again the relations among the rays, okay? This is just to understand the general construction, how to construct, in general, what are the ingredients you need to construct the toric variety, to describe it by a fan. Okay, well, I'm going to fix M rays in standard lattice CQ, if the variety has dimension Q. I'm going to denote by M the number of rays. This is called the skeleton of the toric variety, or the skeleton of the fan. Then another important to fix, in particular in my talk, is a basis of relations among the rays, like the ones in the previous slide, okay? So in general, you have, if the variety has dimension Q and you have M rays, you have in minus Q relations among the rays. I'm going to call them AJ, okay? This is called the Church matrix of the fan. But in fact, it depends on the skeleton, okay? And then you have the rest of the fan that I'm not going to talk more things about this part of the fan. And okay, in general, you can construct a good geometric quotient in the sense of geometric invariant theory. Okay, a toric variety can be described by the affine space Cm when M is the number of rays. You need to raise something here, which can be bigger than the 0 in general. In fact, it's in general, it's a Zariski closed subset of codimension greater or equal than 2. And then you need to take the quotient by certain group G, okay? This can be described in terms of the Church matrix. This can be described in terms of the rest of the fan, and this is the number M here. And again, we have an homogeneous coordinate ring with M variables in this case. And this homogeneous coordinate ring, sometimes called the Cox ring, it's graded by the class group of the variety. The class group of the variety is just the class of Bile divisors among the variety quotient by the principal Bile divisors, okay?
Okay, yeah. In your context, this is always compact, or no?
No, you need to. I'm going to ask to be complete. It depends on the combinatoric of the rays, okay, or the entire fan, in fact. That property depends on the entire fan, on the entire fan, not only on the skeleton, okay? It's just like in the case of P2, the fan must be complete in some sense.
Okay, go ahead.
Okay. Well, also we have for every one-dimensional cone, we can associate a T invariant divisor to B, which will be very important in the rest of the talk. In homogeneous coordinate, these T invariant divisors are just the variable z sub I equal to 0. Okay. And okay, the class group of the variety is isomorphic. The Picard number of the variety is always m minus q. This is the free part of the class group, and then you could have a finite part here. But let me observe that the degree of the variable c sub I, which corresponds to the class of this Weil divisor d sub I in general, are the rows of the Church matrix, numerically speaking. Okay. And then you have here certain part in the finite group H, okay? For example, if the class group is torsion free, this group G that appears here is a torus. It's a torus of dimension m minus q, and can be described as a subtorus of C star to the m using, again, the weights of the Church matrix, okay? Okay, I just want to give you the idea that if you give me the skeleton and the Church matrix, you can describe most of the things that I need in this talk. For example, in the case of surfaces, if you fix the skeleton and you fix the skeleton, there is a unique complete toric surfaces with that skeleton, because you need to paint all the two-dimensional cones. So in the case of surfaces, this is not so important in my talk. Okay, talking about foliations now. How to describe foliations on a toric variety? In general, to describe foliations, you need a line bundle and a twisted differential form. Okay, I'm going to think that a foliation in general is a current subsheaf of the tangent sheaf, which is closed under the Lie bracket. Okay, it's a subdistribution of the it's an integrable subdistribution of the tangent space, and that subdistribution I'm going to think it as the kernel of a differential form. Okay, that's the idea. But in this case, on this toric varieties may be singular. Okay, so the idea is just to consider a line bundle and a twisted differential form on the regular part of the variety. In general, a toric variety is an orbifold, so it has only finite quotient singularities, and the codimension of the singular part is always greater or equal than 2. I'm going to denote by J the inclusion of the regular part into the entire variety. I'm going to work with this GIF of forms called the Zariski forms of the variety. It's just the push forward of the sheaf on the regular part to the entire variety. This is a reflexive sheaf. It consists with a double dual of this differential, this classical differential. The problem is that when you have a singular variety, this sheaf here, the sheaf of differential forms, is not locally free. Okay. Okay. And okay, the other ingredient is to fix a line bundle, but fixing a line bundle on the regular part of a variety is the same as fixing the class of a Weil divisor on the entire variety. Okay. I'm going to assume that this Weil divisor is effective. Okay, with all these ingredients, I'm going to fix a global section of a twisted differential Zariski form by this Weil divisor D here. And I'm going to ask this differential form to satisfy certain equations in order to ensure that the kernel of this differential form as a subsheaf of the tangent sheaf is integrable. And here, for the people which is not from or do not know the standard foliation theory, that conditions ensures that at every non-singular point of alpha, where alpha is not equal to 0, there are maximal solutions with that maximal solution of these equations, in the sense that the tangent space of the solutions is just the space given by this kernel. Okay, these are the integrability equations that we are going to ask here to ensure that this is integrable in that sense. Okay, in order to obtain maximal solution, in this case of codimension k, where k is the degree of the form. Okay. Well, another advantage of working on toric surfaces is that you have a toric-Hilbert sequence, as in the projective space. The interpretation of the Euler-Euler sequence in general is that you can describe these twisted global objects in terms of homogeneous differential forms in the cone, satisfying certain descent conditions, okay? This is the leitmotif of the Toric-Hilbert sequence in general. And here, in this case, we have the radial Euler fields of the toric variety. In the case of Pn, you have only one trivial radial Euler field in the cone that in the variety is equal to 0. In this case, when the variety has dimension q and you have n rays, you have n minus q radial Euler fields. And the coefficients of this radial Euler field can be described again using the Church matrix. Okay, using all this information, I'm going to construct moduli space of singular toric foliations. So how to describe this object, this global section of the sheaf of twisted differential Zariski forms by an effective bidivisor G? Well, in terms of the Cox coordinate or the homogeneous Cox coordinates, you need to fix a K form in the cone, okay, in the cone which is Cm in this case, satisfying that it's homogeneous in the sense of the gradient given by the Cox ring. Okay, I'm going to assume that this differential form has total degree D, where recall that the variable C sub I has degree Di, where Di is the toric invariant divisor associated to the variable C sub I. Okay, this is quite technical perhaps, but you need to fix something homogeneous in the Cox coordinates, okay? And I'm going to ask that this form satisfy that these descent conditions, that its inner contraction by all the radial Euler fields is equal to 0 in order to ensure that well-defined objects in the toric variety. And then I'm going to ask two types of equations in order to ensure that the distribution associated to its kernel is integrable in the sense of foliation theory, okay? The first one is the Placker decomposability condition. Here, these are the Placker equations at each point for this K form, okay? And this is to ensure that outside the singular set, this K form, it's locally the wedge product of K1 forms, okay? This is just to ensure the distribution associated to its kernel has the correct rank, okay? And then we are going to ask something, we are going to ask these integrability conditions, which are a generalization of the standard Frobenius integrability condition. This is to ensure that the distribution associated to the kernel is integrable in the sense that it admits maximal solutions, okay? And with all this information, we can construct moduli spaces parameterizing singular toric foliations on a toric variety X of algebraic degree D here, and of codimension K, okay? It's just projective classes of these homogeneous forms satisfying all these conditions, okay? And also I'm going to ask that the codimension of its singular set, the singular set is just the points where the form is equal to 0. The codimension of this set is greater or equal than 2. These are moduli spaces, yeah.
Javier, this is which K minus 1 times Cm, or this Cm is some X? It's a field, no?
No, I'm going to ask that these forms are satisfied these descent conditions. So these are well-defined singular toric foliations on X, okay? Sometimes we want to see the induced foliation in the cone, but in general, this is a moduli space parameterizing singular foliations on the toric variety.
Something I don't understand. This is Cm. What is this V is what is exactly?
What's the question? I don't know.
V is in the wedge K minus 1 times Cm, and then you contracted differential forms on X by V, which lives in Cm.
Maybe you are asking about this Cm here.
Yeah. What's the relation of this Cm with the toric variety?
No. Maybe this is a typo here. Yeah, no, here it might say, sorry, this is a typo. Here it might be, This is just to fix local frames at each point of the toric variety. Okay.
Okay. So you are taking a section.
Yeah.
In an open
Yeah.
set.
Yeah. Yeah. Sure.
You use a chart of the toric variety. Okay.
Yeah. Exactly. This V here is exactly a local frame at each point.
Okay.
Okay, so one open problem in general, even for the case when x is equals to Pn, is to understand the irreducible components of these moduli spaces and the geometry of these moduli spaces. In the case of Pn, it's only solved for lower degrees d here, okay? That problems of classifying the irreducible components of singular projective foliations, okay? Okay. What we want to do here in this talk is the following, just to follow this idea, okay? What happens if you consider a form or a foliation alpha given by a form alpha in an irreducible component of these moduli spaces and consider a suitable family of rational maps from Pn to our toric variety X and consider its pullback by this rational map? This produces in general a singular projective foliation in the classical sense, in the classical projective space of certain degree d, okay? And the idea is, or one question about this construction is when this construction determines irreducible components of these moduli spaces, okay? My intention here is to study these moduli spaces of singular projective foliations and use this as a key to understand certain irreducible components here. Okay, this is so general, but okay, it's not going to work in general, okay? So how to define rational maps in coordinates? Let me describe these maps here. To define a map from Pn to Pm between two projective spaces, you need to fix m+1 homogeneous polynomials, all of the same degree. This is the standard description of a rational map from Pn to Pm in Cox coordinates. Here, when you have a toric variety instead of Pm, you have a similar description, okay? For when you fix a relation among the rays of the variety X given by certain integral coefficients E1 to Em, if you consider certain homogeneous polynomials, all of degree E sub I, this induces a rational map from Pn to X, okay, according to this diagram here, okay? It's just selecting m homogeneous polynomials of degree E and just put in this rational map in the cone. And this is a well-defined object here between Pn and the toric variety. We're going to say that F is a lifting of this rational map of algebraic degree E. Okay, however, this construction is not perhaps the most general one. Not every rational map between two arbitrary toric varieties can be described in this way. Okay, there is a work where some people describe how to describe rational map between two arbitrary toric varieties. But in our setting, when you put here Pn, this is the correct object to consider. What we can prove in general is that if you have central property in the fan of the toric variety, every rational map from Pn to X can be described, admits a complete polynomial lifting, algebraic polynomial lifting, okay? Where here the word complete means that if you start with a rational map from Pn to X, we have a polynomial lifting with the correct base locus. That the base locus here is just the base locus, the projectivization of the base locus in the Cox, in the affine cone, okay? Okay, well, let me start with the first family of foliations that I'm going to talk about. Okay, first let me recall that for the toric variety X, you can describe easily the canonical sheaf of the toric variety. The canonical sheaf is just the reflexive sheaf associated to this Weyl divisor here. This is the canonical divisor, okay? It's minus the sum of all the toric invariant divisor D sub I. In the case where you are in Pn, for example, all these divisors here are numerically equivalent to 1. So the canonical divisor is minus n plus 1 if you are in Pn. Well, this is a generalization of that fact, okay? And okay, and the object that I'm interested in is the volume form of the toric variety, okay? How to describe the volume form of a toric variety? Okay, you can consider the volume form in the affine cone given by dC1 to the wedge product of dC1 to dCm, and then consider the inner contraction by all the radial fields. In this case, if the variety has dimension q and you have m rays, you have in minus q radial fields. So this is a q form. This is a well-defined q form in the toric variety, and it's the volume form, okay? And the total degree of this form is just the anticanonical divisor given by the sum of all the toric invariant divisors d sub I, okay? Why I'm interested in the volume form? Because I'm going to give you the following definition. If you consider a rational map from Pn to a toric variety of dimension q, we are going to assume that this rational map has a complete polynomial listing. So I'm going to assume that this is a polynomial rational map in the Cox coordinates, okay? I'm going to write f sub f for the foliation given by the fibers of f, okay? Just consider the foliation that in Pn given by fibers of this rational map. This is a singular projective foliation of codimension q. The solutions or the leaves of this foliation is just the fibers of the rational map, and this foliation is singular. You need to erase where the fibers has not the correct dimension, okay? And how to describe these singular projective foliations in terms of an homogeneous differential form? Okay, you can consider the twisted Q form in the projective space given by the pullback of the volume form. So it's easily to describe the foliation and the representation of these foliations in terms of an homogeneous differential form. You can compute this volume form here, and just in the variable c sub I, you can replace it by a polynomial fi according to this description, okay? So using this construction, we can consider a variety of foliations that arise in this way. For every selection of for every selection of an m tuple of homogeneous polynomials of degree e sub I, you can consider this rational parametrization map given by sending each m tuple to the pullback of the volume form. And this determines a foliation here, an element in this moduli space of singular projective foliations of codimension Q. Well, these maps are maybe it's rational. So in order to obtain a closed subvariety of the moduli space of singular projective foliations, I'm going to consider or to define the Zariski closure of the image of this map phi here. Okay, I'm going to use this notation RQ to recall that these are foliations of codimension Q, and here to recall that these determine foliations in the projective space Pn, the toric variety X, and the fixed relation among the rays to determine the rational maps. Okay, so this produces a closed subvariety of this moduli space. And perhaps the first questions to understand is when this construction determines an irreducible component of this. Or in other words, perhaps you can understand when these forms here, omega, satisfies a sort of stability in this space, okay? Well, what happens if you consider X to be a weighted projective space? This construction here determines an irreducible and generically reduced component of the moduli space. This is a work of Kuckerman, Pereira, and Weissencher, okay? They don't, perhaps the description that they make in that paper is not the same description that I give you here. In general, they call these forms, the forms arising in this way, as quasi-rational projective Q forms. This is the standard formulas that they give. For the case where Q is equal to 1, this is the standard formula for a rational form. If you select a homogeneous polynomial f of degree E1, an homogeneous polynomial of degree E2, this produces in general a foliation which is tangent to the fibers of a quasi-rational map, okay? And this produces a singular projective foliation in Pn. And what they do in that paper is to generalize this object here for the case of Q equals to 1 to a general Q. And it's not hard to prove that these two formulas from here coincide with the pullback of the volume form of the corresponding weighted projective space. Okay, so in some sense, the case where X is equal to a weighted projective space have been studied and produce an irreducible component. What happened in the general case? Well, as I said before, it's not hard to compute the corresponding formulas, okay? Because when you have a complete simplicial toric variety, the volume form is just the formula that I give you before. You can consider the volume form in the thin cone and consider the contraction by all the radial Euler fields, R1 to Rn minus Q. If you make that computation, you obtain the following formula, okay? These coefficients here, B, are just an element in this wedge Q of Cm. It's just the inner contraction by the coefficients of the radial Euler fields, A1 to Am minus Q, which are the columns of the Church matrix, in fact, of this standard element, wedge M to Cm, okay? So we produce this formula from here, okay? And also let me observe that these coefficients here, that a priori it's a Q vector in Cm, is totally decomposable in the following sense. It's the wedge product of Q1 vectors, B1 to BQ. And another important fact is that these coefficients here, these coefficients B here, are fixed for a given toric variety, okay? So how to produce our singular projective foliation using these formulas? Well, as I said before, you need to replace the variable C sub I by the polynomials Fi. So you obtain the following, okay? The pullback of the volume form by a rational map F is just the following formula from here. And these formulas from here produce something that has already been studied, are called projective logarithmic Q forms, but with the particular fact that these coefficients here that appear here are constant because they only depend on the toric variety X. Okay, so let me recall some facts about projective logarithmic foliations. The formula of a projective logarithmic foliation is the following. It's the same formula as before, but here, instead of these constant integer coefficients, you can replace them by a general element in this wedge Q of Cm a priori, okay? So let's concentrate in this formula from the right. This is the same formula as before, but here you have a priori certain complex numbers, lambda I. These are called the residues of the form. I'm not going to talk so much things about logarithmic foliations, but this polynomial logarithmic form from here can be written as the product of the following: the product of all the polynomials Fi and a meromorphic form eta here. And this form from here, eta, is just a global section of the standard shift of logarithmic forms over a divisor. Okay, this is the so-called shift of logarithmic forms, and the global section of that shift is what appears here in eta. This is like a regularization of that standard object. Okay. Well, the first question to understand here from this formula from the right is when they satisfy the conditions of the moduli space of singular projective foliations. Okay, if you select the coefficients or the residues lambda and the polynomials f, when the formula from the right define a singular projective foliation, well, the possible answer to that question is that you need to require that these coefficients lambda that a priori are something it's a Q vector, something which Q of Cm, don't pay attention to this E. I'm not going to talk about this, but in general, it's a Q vector of Cm, okay? And we are going to require that this lambda, these coefficients lambda are totally decomposable. They live in the corresponding Grassmannian space. This is the wedge product of Q1 vectors, okay? Asking the coefficients lambda to satisfy these conditions, this formula from the right satisfies the equations of the moduli space of singular projective foliation. In fact, we don't know if this is necessary or not. This is a sufficient condition. We don't know if this is necessary. This is an open question for the case when Q is greater than 2. Okay. this is part of of my PhD work. Okay, so this is the reason that I'm going to not talk so much about now. Okay, so using this formula, we can proceed as before. Okay, you can consider this rational map parameterizing this type of foliations, just considering the coefficients lambda and the polynomial f. This is again a rational map, and you can consider the logarithmic varieties to be the Zariski closure of the image of this map. Okay, and a theorem that appears in my PhD thesis and was generalized by Cerveau and Lisneto is that this in general construct irreducible. In my PhD thesis, I proved this fact for the case of equals to 2. And Cerveau and Lisneto generalized this fact to an arbitrary Q. Okay. So coming back for our family of singular projective foliations that arise as pullbacks or foliations given by the fibers of toric pullbacks or toric rational maps, we have the following. Okay, if you have a toric variety of dimension q and you have m raised in the lower possible case for m, which is q plus 1, you have only 2 complete toric varieties with that number of rays: the projective space, a weighted projective space, or a fake weighted projective space. This is the quotient of a weighted projective space by a finite group. Okay, these are the only 2 possibilities when m is equals to q plus 1, and in both cases you obtain an irreducible component of the corresponding moduli space. This is the quasi-rational case that I explained before. In the case when m is greater than q plus 1, you have that this variety that we construct lives inside a logarithmic variety. Okay, it lives inside, it's a subset, it's a closed subset of a logarithmic component. And what we can prove is that in general this inclusion from here is proper. Okay, so the only case where this variety of foliations that arise at the fibers of rational maps to in these varieties fills an irreducible component of the corresponding moduli space is when the variety xq is a weighted projective space or a weighted projective space. And the idea of the proof is just to prove that the Zariski tangent space of these varieties is the inclusion in the Zariski tangent space of the logarithmic component is proper. Okay, so this inclusion in general is
weighted.
What?
What is fake weighted projective space?
Yeah, okay. Fake weighted projective space is the quotient of a weighted projective space by a finite group.
Okay.
But in our, I don't explain it so much, but you have this in some sense is the class group of this variety is free, and the class group of this variety is not free. For every toric variety with a class group with torsion, you have a version without torsion. And this is the corresponding between this variety here and this variety here. But yes, a fake weighted projective space is the quotient by a finite group of a weighted projective space. And these are the only 2 varieties with this number of rays in the corresponding fund. Okay, when we prove this inclusion between the Zariski tangent spaces, in particular, we can compute the dimension of the corresponding Zariski tangent space, and we prove a result of independent interest. We compute the dimension of this logarithmic varieties, the case equals to 2, because we can compute the corresponding Zariski tangent space. Okay, I don't know how much time I have, perhaps 10 or 15 minutes. I'm going to talk about the last family of singular projective foliations that we have in our work. This is another construction. I'm going to assume now that X is a complete simplicial toric surface. What's the advantage of working on a toric surface? Well, perhaps the advantage is the following, that these moduli spaces of singular projective foliations, in the case of codimension 1, these are 1 forms, okay, in our complete simplicial surface. This trivially satisfies the integrability condition, because in the case of q equals to 1, the integrability condition is just alpha wedge d alpha equals to 0, but this is always equals to 0 because it's a twisted free form in the variety, and the variety is a toric surface, so this is always equal to 0. So this moduli space is just an offset of this projective space, of this affine space here. So the only equations that we need to ask to our forms alpha in the affine cone are the descent conditions, because the integrability conditions are trivial. And these are linear equations for the polynomial coefficients of alpha, given by the inner contraction of Euler radial Euler fields, okay? So these are the only equations that you need to require. But we have another way to not ask in this question. We can parameterize the polynomial satisfying these equations using the following fact. By duality, every one form on a toric surface can be described, or the foliation associated to a one form in a toric surface can be described also by a homogeneous vector field in the variety. So if we consider an homogeneous vector field and consider the form alpha given by the inner contraction by this field of the volume form, in some sense, you obtain all the polynomials AI that satisfy the descent conditions. So here, the coefficients of the homogeneous vector field Y are free in some sense. The only problem is that, for example, in the cone, the radial vector fields in this construction gives the foliation just given by the trivial foliation. It's the zero foliation. It's not a foliation. So this vector field here are well defined up to the sum of a combination of the radial Euler fields. Okay. So let me observe that here appears again the coefficients of the volume form, okay, which are fixed for every complete simplicial toric surface. Well, we are going to proceed as before. For every rational map with a polynomial lifting of degree E, we are going to consider the pullback of these forms from here. And we produce a singular projective foliation of certain degree, algebraic degree. If our toric divisor is effective, it's a combination of the T invariant divisors by the D sub I with positive coefficient Di. And the number that appear here in the singular projective foliation is just the inner product of these coefficients D with the coefficients or the degrees of the polynomial Fi, okay? We are going to assume that in some sense, this form alpha here and this polynomial F from here are generic in some sense, okay? So again, we can produce varieties foliation given by pullbacks in the same way. Using parameters alpha and polynomials Fi, you can consider the pullback given by the map F of this form alpha and produce singular projective foliations. Again, this is a rational map. I'm going to consider the Zariski closure of the image of this map. I'm going to denote this by these varieties, okay? PV1 NXDE. This one here says that this produces codimensional 1 foliations on a projective space of dimension n, given by a toric surface X, with algebraic degree D given by effective by divisor, and where the degree of the rational maps is given by E. So a natural question that arises is when these constructions produce irreducible components.
Excuse me, Javier. What do you mean by G? What is G, please?
What is G? Okay. You need to, in some sense, okay, maybe I could erase this here, but G has a natural action on the affine space CM, okay? It's the group of the toric variety, okay? So
I see. Thank you.
Okay. You can act with the polynomials, okay? Just indicating the action of G on CM minus C, okay? But it's not important because this map is rational. So perhaps if you don't put this G here and this C here, this is well defined also because this is rational, okay? So there are some examples of this construction that produce irreducible components. For example, this is a classical result of Servolis-Neto and Etzhoven. When you put here as X equals to P2, this produces irreducible components called the pullback components. What happens when you put a weighted projective space Q2 with weights A. Well, for example, if the degree that appears here is the sum of the weights, this produces a logarithmic component. Okay, I'm going to generalize this result now. Okay. Okay. Let me observe that this degree that I put here, the sum of arrays, in the case of a weighted projective plane, is just the anti-canonical divisor. It's the degree here associated to the effective Weil divisor given by the anti-canonical divisor. If you consider the vector fields E to be linear, it determines rational components. Okay, so in general, it's not hard to compute these varieties, okay? Because to compute the corresponding formulas of generic element in these varieties, you can put weighted projective surfaces, Hirzebruch surfaces, blow-ups, and different type of projective or toric surfaces. The question is when determine components. This is so general. The answer, perhaps the answer to this question is not always, okay? And let me show you an example, generalizing this from here. What happens if in a toric surface you consider the degree given by the anti-canonical divisor? When you consider the anti-canonical divisor here, this is contained in the variety of logarithmic forms, okay? And it happens something very similar to the problem that I described for pairs of rational map. This is contained in a logarithmic variety, and this contention is proper, perhaps always, except when you consider X to be a weighted projective surface or a weighted projective surface. In any other case, the illusion is proper. Okay. And the idea is that, again, when you are in a surface, the lower number of rays is m equals to 3. When the number of rays is 3, you keep the surface with 5 weighted projective spaces. In any other of rays is higher than 3. And okay, you have the formulas from the elements in these pullback components are just these logarithmic formulas again. But the problem, just for the people that know about logarithmic forms, the corresponding residues lambda I satisfy more descent conditions than usual, because you need to consider the contraction by more radial Lagrange fields than usual. Okay, this is just an idea of the proof. Okay, but this is something that say you that, for example, in the case when you consider here the anti-canonical divisor, this construction maybe not produce irreducible components, except in this case, the case of a weighted projective surface or a fake weighted projective. Okay, I don't have so much time to explain the rest of the work because it's too large, but let me just say what we do in 5 minutes or maybe less. We study the singular scheme of singular projective foliation given by this object, okay? So perhaps I can tell you something of a foliation and stop there. When you have a singular projective foliation in a toric variety of dimension Q given by this homogeneous form alpha, the singular scheme is just the singular set of the foliation is just the zero is where the coefficients, these polynomial coefficients vanish. So we can associate a scheme to that algebraic variety given by the ideal just generated by the polynomial coefficients of the form. And the singular scheme is just the ideal, just is the scheme associated to this homogeneous ideal. A study in our work is something important, certain type of singularities of this form, which are called Kupka. But in general, a Kupka point of a differential of the singular set of a foliation is a Kupka point is just a point in a singular set where the exterior derivative of the form is not equal to 0. These are the Kupka points here by k sub 0. Okay, Kupka set of the singular of the singularities of the form is just the Zariski closure of this set, this open set. This is just a description of the Kupka variety set theoretical. In order to construct the Kupka scheme, what we can do a schematic support of the form D alpha. You can consider the ideal given by the quotient ideal of the coefficients of alpha transported or quotient by the coefficients of the alpha. This produces an homogeneous ideal, which is the schematic support of this, what we are going to call the Kupka scheme. And the problem with the Kupka scheme is that perhaps this, the support of the Kupka scheme is not the Kupka set. Something very complicated, but when the singular scheme, the singularities of alpha are reduced, so this ideal here is radical, the Kupka set coincides with the Kupka scheme. And what we do in part of our work is to study the singular scheme and the Kupka set of singular projective foliation given by pullbacks of foliation from surfaces. And in the last part of our work, what we study is deformations of this object, okay, in order to understand when they determine irreducible components. In the case of the description of the singular and the Kupka scheme, we have a complete description of these schemes in the case of pullbacks of foliations of toric surface. In the case of deformations, we could result describing when this construction determines or not irreducible components, but we have to understand perhaps in what cases you can obtain irreducible components and in which case, okay? Hussein, you need to go to meeting from impact. So the talk, and if you know, if you want to know something about that last part that I talk, you can ask me, and I could say something. Here are the references. Okay, thank you for listening.
Okay, thank you, Javier. A question. I'll see this. If you want a question, you can type in the chat, or if you want, you can send me WhatsApp, and I can reproduce your question. I don't know. Anyway, if nobody has question, I have one question. Okay. Actually, it is a comment. I mean, it makes also to do in dimension 2. And in dimension 2, when you make the pullback of foliation surfaces to P2, you will produce something called center singularity, whose leaves is exactly the logo of the seminar. They are in this case also we have the space of foliations with center singularity, which its classification is more complicated than this higher dimensional one. But I think it would be at least nice to reproduce some conjectural component in this way. Take some toric surface, make it pull back, and try to see whether in dimension 2 also this produces irreducible component.
Okay.
But this is one, and again, once again, I have something that I am against, that you call it moduli space. It's parameter space, because
Okay. I know.
It's like taking curves in P2 and taking talking about parameter space as moduli space. The moduli space of curves is not just the coefficients of
it's
the
moduli space in the sense that in the sense that they parameterize singular foliations. Okay.
But anyway, okay. Actually, this is a very good question. Well, with the moduli, if somebody has studied the moduli space of foliations, in the sense that you make the quotients over the automorphism of P2,
yeah,
and to see which kind of a space it is.
Yeah, in the sense of it. Yeah.
And so on. Okay.
Yeah.
No more questions. Let's see. Okay, if there is no question, let's thanks again Javier for his talk with Okay, so see you next week, and Lubomir will talk about some actually foliations in P2, but from a different point of view. Thank you.
Okay.
Bye-bye.
Bye.
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 Javier,
Sí, Rubén.
escucha, dime,